Have you ever wondered what lies at the very edge of our solar system? Beyond Neptune, beyond the familiar planets, there exists a realm so distant that sunlight takes more than 5 hours to reach it. This is the domain of Pluto and the Kuiper Belt, a place where ancient ice preserves secrets from the birth of our world, where mountains made of frozen water tower kilometers high, where a dwarf planet harbors an ocean beneath its frozen heart. For decades, we imagined this frontier as a lifeless wasteland. But when we finally sent a spacecraft to visit, everything changed. Join me now on a journey 3 billion miles from home. Let the vastness of space calm your mind as we explore the most surprising worlds in our cosmic neighborhood. Our journey begins here on Earth, but our destination lies 40 times farther from the sun than we are. To understand what that means, imagine standing on a beach holding a grain of sand. That grain represents Earth. The sun would be a beach ball 30 meters away. Pluto? It would be more than a kilometer down the shore. The distance is almost incomprehensible. Yet in January of 2006, humanity launched a spacecraft the size of a grand piano toward this distant realm. We called it New Horizons, and we gave it a singular mission to finally see what had remained hidden in the darkness for all of human history. The spacecraft accelerated faster than anything humanity had ever built. 16 kilometers every second. Within 9 hours, it passed the moon, a journey that took Apollo astronauts 3 days. It crossed the orbit of Mars within months. Then came years of silent coasting through the empty darkness between worlds. Can you imagine that patience? Nearly a decade of waiting, hoping, trusting that every system would work perfectly when the moment finally came. The engineers who designed it would grow older. Children born the day it launched would be finishing elementary school when it arrived. Yet the spacecraft flew on, unwavering in its purpose. As New Horizons traveled farther from the sun, the light grew dimmer. The warmth we take for granted faded into profound cold. At Pluto's distance, the sun appears as merely the brightest star in the sky. It provides only 1,000th the light that bathes Earth. Imagine standing outside on a sunny day, then reducing that brilliance to the equivalent of a single candle held at arm's length. This is the perpetual twilight in which Pluto exists. And yet, as we would discover, this distant world is anything but dark or dead. It glows with its own ethereal beauty, sculpted by forces we never imagined could exist so far from the sun. In the final months before arrival, Pluto began to transform from a single pixel into a world. First, just a blur. Then, tantalizing hints of bright and dark regions. Scientists and the public alike held their breath as features emerged. A strange, bright area shaped like a heart, dark streaks and mysterious patterns. With each passing day, with each new image transmitted across billions of kilometers of space, anticipation built. What would we find? Would Pluto be just another cratered, dead world like so many moons we had visited? Or would it surprise us? As the spacecraft prepared for its historic encounter, the entire world watched and wondered. On July 14, 2015, at nearly 8 in the morning Eastern Time, New Horizons screamed past Pluto at more than 50,000 kilometers per hour. Came within 12,000 kilometers of the surface, closer than the width of Earth. For a few precious hours, every instrument pointed at this mysterious world, gathering data as fast as possible. There would be no second chance. No orbit, no return visit. Just one perfect flyby. And in those hours, everything we thought we knew about the outer solar system changed forever. The first images arrived slowly. Remember, light itself takes more than 5 hours to travel from Pluto to Earth. Radio signals carrying pictures moved at the same leisurely pace, and the spacecraft could only transmit at about 1 kilobit per second, slower than the oldest dial-up internet connections. It would take 15 months to download all the data. But when those first high-resolution images appeared on screens around the world, they revealed something nobody had predicted. Pluto was not a boring ball of ice. It was a world of breathtaking complexity and stunning beauty. A world that defied every expectation. What drove us to make this journey? Why spend nearly $1 billion and nearly 10 years to visit a world so small and so distant? Perhaps because exploration is fundamental to who we are. Because the unknown calls to something deep within us. Because every time we have looked beyond the horizon, we have found wonders that expanded our understanding of existence itself. Pluto represented the last of the classical planets to be visited, the final destination in our initial survey of the Sun's family. And as we are about to discover together, it was worth every mile, every year, every effort. The most striking feature on Pluto dominates the hemisphere. New horizons encountered. A vast heart-shaped region, brilliant white against the darker surroundings. Scientists named it Tombaugh Regio, honoring Clyde Tombaugh, who discovered Pluto in 1930. This heart measures roughly 1,600 kilometers across. To put that in perspective, you could fit Texas and Oklahoma inside it. The western lobe of this heart, called Sputnik Planitia, would prove to be one of the most extraordinary features in the entire solar system. As we draw closer, let your mind settle into the serene beauty of this frozen plain stretching to the horizon. Sputnik Planitia is a basin, a depression in Pluto's surface about 3 to 4 kilometers deep, and it is filled not with water but with nitrogen ice. Solid nitrogen, as smooth and flowing as a glacier. The basin stretches 1,400 kilometers by 1,200 kilometers, and scientists estimate the ice layer measures several kilometers thick. At Pluto's surface, temperature of negative 233 degrees Celsius, nitrogen behaves like rock does on Earth. And flow. It can flow and crack. It can even, in its own slow way, convect. This is the largest glacier in the known solar system. Look closely at Sputnik Planitia's surface. Do you see the pattern? The plain divides into irregular polygons, each about 33 kilometers across. These cells resemble the mud cracks in a dried lake bed or the pattern of convection cells in a pot of slowly boiling water. And that second comparison is remarkably accurate. The nitrogen ice is convecting. Warm ice from below rises in the centers of these cells at about 7 to 14 centimeters per year. Cool ice at the edges sinks back down. This slow overturning completely resurfaces the plain every 500,000 years, erasing any craters that might have formed. But nitrogen ice is not the only ice here. Mixed within it are smaller amounts of carbon monoxide and methane, both frozen solid at these temperatures. And look at the borders of Sputnik Planitia. What do you see rising there? Mountains. Enormous mountains made of water ice. At negative 230 degrees, water ice becomes as hard as granite. The Tenzing Montes rise more than 6 kilometers high, taller than Alaska's highest peak. The Hillary Montes reach 3.5 kilometers. These mountains may actually float on the denser nitrogen ice below, like icebergs in a nitrogen sea. Why does Sputnik Planitia convect when it is so far from any heat source? Scientists believe the answer lies in a paradox. The surface of the ice is actually being cooled by sublimation. As nitrogen evaporates directly from solid to gas, it consumes energy, cooling the surface layer. This cold, dense ice then sinks, while deeper, slightly warmer ice rises to replace it. The entire system is driven not by heat from below, but by cooling from above. It is a type of convection never definitively observed anywhere else in the solar system. A reminder that the universe finds ways to surprise us. The location of this heart is not random. Sputnik Planitia sits almost exactly on the tidal axis between Pluto and its large moon Charon. How did it end up there? The answer involves something called true polar wonder. When the basin formed, likely from an ancient impact, it filled with ice. That ice was less dense than the surrounding rock and ice, creating a mass deficit. Over millions of years, Pluto's entire crust rotated, moving the basin to align with the tidal axis where the mass anomaly creates the least stress. The whole world reoriented itself like a spinning top adjusting to a weight on its edge. This reorientation tells us something profound. For true polar wonder to work, Pluto must either have an extremely thin ice shell or something even more remarkable, a subsurface ocean. A layer of liquid water sandwiched between the surface ice and the rocky core below. The math only works if that ocean exists, allowing the crust to move independently of the interior. Could there really be liquid water on a world so cold, so far from the sun? As we will discover, the evidence grows stronger with every measurement. Pluto may be an ocean world. Beyond the smooth plains of Sputnik Planitia, Pluto's landscape becomes wild and complex. Everywhere we look, we see features that speak of geological activity. Oh. But how can that be? How can a world barely 2/3 the diameter of our moon, receiving 1/1000th the sunlight of Earth, remain geologically active? The answer lies partly in ice itself. Not water ice, but volatiles like nitrogen and methane that can flow and reshape the surface even at these extreme temperatures. And partly in internal heat that we are only beginning to understand. Let us explore these frozen mountains and mysterious volcanic features together. Let me take you to a place called Right Mons. It rises as a broad dome 150 kilometers across and 4 to 5 kilometers high. At its summit lies a depression, a pit 40 to 50 kilometers wide. This is not an impact crater. The shape is wrong, the setting inappropriate. Scientists believe Right Mons is a cryovolcano, an ice volcano. Not erupting molten rock, but some mixture of water ice, ammonia, and perhaps nitrogen. The term volcano feels strange, applied to something so cold, yet the principle remains the same. Material from below rises to the surface, driven by buoyancy and pressure, reshaping the world. Nearby stands Picard Mons, perhaps even more impressive. 225 kilometers wide and 7 kilometers tall, it may be the largest cryovolcanic feature in the entire solar system. These structures lack the abundant small craters that cover older surfaces. Either they formed relatively recently or they have been resurfaced since their creation. Recent in geological terms might mean a few 100 million years, which sounds like forever but represents only a small fraction of Pluto's 4.6 billion year history. Something has kept these regions young. Something continues to drive change on this distant world. The most compelling evidence for cryovolcanism comes from a region called Virgil Fosse. Here, New Horizons detected the spectral signature of ammonia mixed with water ice. This discovery matters because ammonia is fragile. Solar radiation and cosmic rays should break it down within 10 to 10,000 years. Yet there it is, clearly visible. The only explanation is that the ammonia arrived recently, brought to the surface by cryovolcanic eruptions. Imagine these vents opening, releasing slurries of water and ammonia that float across thousands of square kilometers before freezing solid. It suggests Pluto's interior remains active even now. What provides the heat for this activity? Pluto formed more than 4 billion years ago. Any heat from its formation should have long since radiated into space. The most likely answer is radioactive decay. Deep in Pluto's rocky core, uranium, thorium, and potassium slowly break down, releasing heat. It is not much, just a few milliwatts per square meter. But over billions of years, in a small world with good insulation, it can be enough. Add in the antifreeze effect of ammonia mixed with water, and you have conditions where liquid water can persist at temperatures far below 0 degrees Celsius. Not all of Pluto's mountains are volcanic. Some formed through other processes. Extensional faulting created long ridges and valleys where the crust pulled apart. These features suggest Pluto has expanded over time, perhaps as an internal ocean froze and the ice expanded, cracking the overlying crust. It is the same process that causes water pipes to burst in winter, but on a planetary scale. Every crack, every valley, every mountain tells part of the story. And that story is one of a world far more dynamic than we ever imagined. A world that continues to evolve even today. Take a moment to absorb what we have found here. A world smaller than our moon, orbiting 40 times farther from the sun than Earth, with less sunlight than a single candle provides. Yet it possesses flowing glaciers, towering mountains, and likely active ice volcanoes. It challenges our assumptions about where geological activity can occur. It expands our understanding of what makes a world dynamic. And it hints that many other distant frozen worlds might harbor similar surprises. The universe, we are learning, is far more active, far more alive than we once believed. And we have only begun to explore. Beneath the frozen surface, beneath kilometers of solid ice, something remarkable may exist. Something that transforms our understanding of Pluto from a dead ball of rock and ice into something far more intriguing. Liquid water ocean? Hidden in the darkness, insulated from the cold of space, this ocean might be as large as the Great Lakes combined, or perhaps even larger. How do we know it exists if we cannot see it? Through clues scattered across the surface, through careful measurements and mathematical modeling. Let me show you the evidence piece by piece and you can judge for yourself. The first clue comes from that heart-shaped basin we explored earlier. Remember how Sputnik Planitia sits precisely on the tidal axis? For true polar wonder to move it there, the crust must be able to rotate independently of the interior. This only works if there is a decoupling layer between them. A liquid layer. Recent computer models suggest this ocean might lie 100 to 200 kilometers beneath the surface, with the ice shell above being only 40 to 80 kilometers thick. Those numbers come from matching the observed shape and location of features on Pluto's surface. The second clue comes from extensional features across Pluto's surface. These long cracks and valleys suggest the world has expanded. Why would it expand? If a subsurface ocean gradually freezes, the ice takes up more volume than the liquid water did. This expansion cracks the overlying crust, much like a freezing bottle of water shatters its container. The pattern and extent of these features allow scientists to estimate how much water has frozen and how much might remain liquid. The calculations suggest an ocean could still exist, especially if it contains antifreeze like ammonia that lowers the freezing point. If this ocean exists, what might it be like? Scientists believe it would be salty. Perhaps as salty as Utah's Great Salt Lake, about 8% denser than Earth's seawater. The pressure at its base would be immense, though nowhere near Earth's ocean depths. The darkness would be absolute. No light has reached this depth in billions of years. And the temperature would hover just above freezing, kept liquid by the presence of ammonia or other salts acting as antifreeze. It would be a strange ocean indeed, but an ocean nonetheless. Liquid water persisting billions of kilometers from the sun. How could such an ocean remain liquid for billions of years? The answer involves remarkable insulation. A layer of methane clathrate hydrates, gas molecules trapped in ice cages, might cover the ocean like a blanket. This layer would have thermal conductivity 5 to 10 times less than regular water ice. Combined with the heat from radioactive decay in the core below, it could be enough. Enough to keep water liquid. Enough to maintain an ocean on a world that should be frozen solid. Nature, it seems, is more clever than we anticipated. More capable of preserving conditions we associate with life. Could life exist in such an ocean? You do not know. Life requires liquid water, energy, and the right chemistry. Pluto might have all three. The ocean provides the water. Radioactive decay and tidal friction provide energy, and interactions between the ocean and the rocky seafloor below could provide the chemical nutrients life needs. We have found life in Earth's deepest, darkest oceans, thriving around hydrothermal vents that never see the sun. Could something similar exist beneath Pluto's ice? It seems unlikely, but unlikely is not impossible. And that is a profound thought. If Pluto has an ocean, we must rethink what we mean by ocean worlds. Europa and Enceladus maintain their oceans through tidal heating from Jupiter and Saturn. But Pluto receives no such assistance. Its ocean, if it exists, persists through internal heat alone. That means ocean worlds might be common throughout the outer solar system and around other stars. Everywhere ice and rock coexist, radioactive decay could maintain hidden seas. The implications expand the number of potentially habitable environments in the galaxy by orders of magnitude. And it all begins here, with this small, distant, surprising world at the edge of our solar system. You might think a world as small and cold as Pluto could not hold an atmosphere. But you would be mistaken. Pluto possesses a thin but extensive atmosphere, primarily nitrogen with traces of methane and carbon monoxide. The surface pressure is about 10 microbars, roughly 100,000 times less than Earth's. That is comparable to the pressure 60 kilometers above Earth's surface in the mesosphere. Yet this tenuous atmosphere extends hundreds of times higher than Earth's, reaching 1,600 kilometers above Pluto's surface. Why? The answer lies in the weakness of Pluto's gravity and the atmosphere's behavior at such extreme cold. The atmosphere is not uniform. It varies with the seasons, which on Pluto last decades. When a region enters sunlight after a long winter, nitrogen ice sublimates, evaporating directly from solid to gas. This increases atmospheric pressure. When the region enters shadow, the nitrogen freezes out onto the surface. Pluto breathes, you might say. Inhaling and exhaling atmosphere as it orbits the sun on its 248-year journey. Scientists predicted the atmosphere might collapse as Pluto moved farther from the sun after its closest approach in 1989. But it has not collapsed. Not yet. The atmosphere persists, maintained by processes we are still working to understand. The atmosphere contains an unusual feature. About 20 distinct haze layers, suspended at various altitudes. These hazes consist of tholins, complex organic molecules created when solar ultraviolet light breaks apart methane and nitrogen. The molecules recombine into larger structures, then aggregate into tiny particles that scatter light. The hazes give Pluto's atmosphere a bluish tint when backlit by the sun. It is the same physics that makes Earth's sky blue and explains the color of Titan's atmosphere. Even in the outer solar system, even at negative 200 degrees, organic chemistry happens. The building blocks of life form naturally. A temperature inversion exists in the lower atmosphere. The surface sits at about 40 Kelvin, negative 233 Celsius. But 30 kilometers up, methane's greenhouse effect warms the air to 110 Kelvin. The atmosphere is warmer than the ground beneath it. This inversion affects how gases move and how particles settle. It is one reason the atmosphere extends so high. Without this warming, the atmosphere might be denser and more compact. Instead, it is diffuse and extended, reaching well into space. Every detail we measure reveals new complexity, new physics operating at these extremes. Scientists expected Pluto's atmosphere to be escaping rapidly into space. The escape velocity is low, and so the radiation should heat the upper atmosphere enough to drive hydrodynamic escape. But New Horizons measured the actual escape rate at only 10,000 times slower than predictions. Pluto has lost only a few centimeters of nitrogen ice over its entire 4.6 billion year history, not the meters expected. Something is wrong with our models. Perhaps cooling by molecular interactions is more efficient than we thought. Or perhaps Pluto's interaction with its large moon, Charon, affects atmospheric dynamics in ways we do not yet understand. Methane ice dunes were discovered near the edge of Sputnik Planitia. Dunes, on a world where the atmosphere is 100,000 times thinner than Earth's. Winds should be far too weak to move particles. Yet there they are, ridges of methane ice grains, spaced about 1 kilometer apart, stretching 75 kilometers across. How? The answer involves sublimation again. Nitrogen ice evaporates. It lofts the lighter methane particles. Then winds of about 30 kilometers per hour, possible even in this thin atmosphere, transport and deposit them. It is a process unique to these conditions, teaching us that landscapes can form in ways we never imagined. Let yourself marvel at this thin shell of gas surrounding Pluto. This atmosphere that should not exist by our simplest calculations. This layer, where organic chemistry creates the building blocks of life. This dynamic envelope that breathes with the seasons and extends hundreds of times its world's radius into space. It reminds us that atmospheric science is not simple, that every world has its own story, that the universe operates according to physical laws, yes, but with endless variations on the theme. And each variation teaches us something new, makes us reconsider what we thought we knew, expands our understanding of what is possible. Pluto does not journey through space alone. It has a companion, a moon so large compared to Pluto itself that the two form what astronomers call a binary system. This moon is Charon, discovered in 1978. It measures 1,200 kilometers in diameter, slightly more than half Pluto's size. If our moon were proportionally that large compared to Earth, it would be 5,000 kilometers across instead of 3,500. Charon contains about 1/8 of Pluto's mass. The two orbit not around a point inside Pluto, but around a point in space between them. They dance together, locked in an eternal embrace. The center of mass around which both bodies orbit sits about 2,000 kilometers from Pluto's center. Since Pluto's radius is only 1,200 kilometers, this point lies almost 1,000 kilometers above Pluto's surface. Both worlds orbit this external point every 6.4 days, and both are tidally locked to each other. Pluto always shows the same hemisphere to Charon. Charon always shows the same hemisphere to Pluto. From Pluto's near side, Charon hangs perpetually in the same spot in the sky. From Charon's Pluto-facing hemisphere, the dwarf planet similarly never rises or sets. This mutual tidal locking is rare, shared only with the distant Eris and its moon Dysnomia. Charon's surface tells a different story than Pluto's. Where Pluto is covered with nitrogen, methane, and carbon monoxide ices, Charon's surface consists primarily of water ice. Pluto appears reddish-brown in places, bright white in others. Charon is mostly grey, with one dramatic exception. Its north polar region, called Maunder Macula, appears dark reddish-brown. This color comes from tholins, organic molecules formed when solar radiation processes methane and nitrogen. But where does the methane come from? From Pluto. Some of Pluto's escaping atmosphere gets captured by Charon's gravity, condenses at the cold polar regions, and radiation converts it to these complex organics. Charon experienced dramatic tectonic activity early in its history. Enormous canyons cut across its surface. Caluche. Chasma extends at least 350 kilometers and reaches 14 kilometers deep. For comparison, Earth's Grand Canyon is less than 2 kilometers deep. Argo Chasma potentially reaches 9 kilometers deep, rivaling Verona Rupes on Miranda as one of the tallest cliffs in the solar system. Serenity. Chasma forms part of an equatorial belt of gravens and scarps extending at least 1,000 kilometers. These are extensional features formed as Charon's interior expanded. Why did it expand? Early in its history, Charon likely possessed a subsurface ocean, just as Pluto might today. Heat from formation and radioactive decay kept water liquid beneath the crust. But Charon is smaller than Pluto with less radioactive material in its core. Over about 2 billion years, the ocean slowly froze. As water turned to ice, it expanded. The volume increase cracked the overlying crust, creating the enormous canyons we see today. Charon's surface records this expansion, this transformation from ocean world to frozen world. Looking at these ancient scars, we see Charon's death as an active world. It has been geologically dead for billions of years. The formation of the Pluto-Charon system likely involved a giant impact billions of years ago. A proto-Pluto collided with another large icy body. The impact was not violent enough to completely shatter both objects. Instead, they temporarily stuck together in a contact binary, rotating as a single elongated object. The collision generated heat, perhaps even creating pools of liquid water near the impact site. Eventually, the objects separated while remaining gravitationally bound. Tidal interactions circularize the orbit over millions of years. This scenario explains the similar densities of Pluto and Charon, the binary nature of their orbit, and the presence of Pluto's 4 smaller moons, likely formed from impact debris. When you look at Pluto and Charon, you see a unique relationship in our solar system. 2 worlds locked in an eternal dance, forever facing each other across 19,000 kilometers of space. One still geologically active with flowing ices and possible oceans. The other frozen and dead, its surface a record of ancient convulsions. Together, they form a laboratory for understanding how worlds evolve differently despite similar origins. How size matters, how heat is retained or lost. How time transforms landscapes. They remind us that every world has its own story, and every story enriches our understanding of how planets work, here and everywhere. Pluto is not alone in the outer darkness. It is merely the largest known member of a vast population of icy bodies. We call this region the Kuiper Belt, and it represents one of the largest structures in the solar system. Beginning at Neptune's orbit, 30 astronomical units from the Sun, the belt extends outward to approximately 50 astronomical units. Remember, 1 astronomical unit is Earth's distance from the Sun, about 150 million kilometers. So we are talking about a region that begins 4.5 billion kilometers from the Sun and extends another 3 billion kilometers beyond that. A realm of frozen time. The Kuiper Belt is not a thin ring like Saturn's. It is more like a thick disk or torus, puffed up above and below the plane of the planets. Current estimates suggest 200 to 300,000 objects larger than 100 kilometers across. Millions to trillions of smaller bodies. But most of the original belt is gone. When the solar system was young, the Kuiper Belt likely contained 7 to 10 Earth masses of material. Today it holds only about 2% of an Earth mass. What happened to the rest? It was scattered by Neptune when that planet migrated outward about 4 billion years ago. Some material went inward, some outward, some was ejected from the solar system entirely. The Kuiper Belt divides into several populations. Classical Kuiper Belt objects follow nearly circular orbits between 40 and 50 astronomical units, unperturbed by Neptune. These divide further into cold classical objects with very circular low inclination orbits and hot classical objects with more elliptical tilted orbits. Despite the names, cold and hot refer to orbital energy, not temperature. Everything in the Kuiper Belt sits at about 40 Kelvin, negative 230 degrees Celsius. The orbital classifications tell us about the body's histories, about which objects formed where they are now versus which were scattered from elsewhere. Resonant objects are locked in orbital resonances with Neptune. Pluto itself belongs to the largest group, the Plutones, in a 3:2 resonance. They complete 2 orbits for every 3 Neptune orbits, always maintaining the same geometric relationship. This resonance actually protects them from close encounters with Neptune that might eject them from the solar system. Other resonances include the 2:1, the 4:3, and the 5:3. Each resonance traps thousands of objects. Understanding these resonances helps us reconstruct the solar system's history, particularly Neptune's migration that shaped the entire outer solar system 4 billion years ago. Beyond the classical belt lies the scattered disk, extending from 30 astronomical units to nearly 1,000. Objects here follow highly eccentric orbits that bring them near Neptune at closest approach, but carry them hundreds of astronomical units away at their farthest. These objects are actively being scattered by Neptune. Their orbits are not stable. Over millions of years, they will either be ejected from the solar system, impact a planet, or be captured into a shorter orbit. Some scattered disk objects become centaurs, transitional objects between the Kuiper Belt and inner solar system. Eventually, some become Jupiter family comets, icy bodies that brighten spectacularly as they approach the sun. Detached objects occupy a mysterious realm beyond even the scattered disk. These bodies have perihelia too distant for Neptune to influence. Sedna orbits from 76 astronomical units to 937 astronomical units over 11,000 years. It never comes close enough to Neptune for that planet to have scattered it to its current orbit. Oh, how did it get there? Perhaps a passing star perturbed it when our sun was still in its Earth cluster. Perhaps a planet-sized object ejected from the solar system in its youth pushed Sedna outward. Or perhaps an undiscovered planet, Planet 9, lurks in the darkness, its gravity shaping the orbits of these distant wanderers. The Kuiper Belt preserves material from the solar system's birth. Protected from solar heating, shielded from most collisions by their vast separation, these objects are time capsules. They contain the original ices, the original organic materials, the original minerals that condensed from the solar nebula 4.6 billion years ago. By studying them, we study our origins. We learn how the sun and planets formed. We understand what conditions were like at the dawn of the solar system. And we see that planet formation left behind debris, scattered populations, evidence of its violence and complexity. The Kuiper Belt is not just a collection of rocks and ice. It is a library, and we are only beginning to read its pages. The Kuiper Belt contains other large objects, some nearly rivaling Pluto in size. These dwarf planets each have their own stories, their own mysteries. Let me introduce you to a few. First, Eris. Discovered in 2005, Eris measures 2,300 kilometers across, slightly smaller than Pluto, but 27% more massive. It was Eris's discovery that triggered the debate leading to Pluto's reclassification. Eris orbits on a highly elliptical path that takes it from 38 to 98 astronomical units over 560 years. Its orbit tilts 44 degrees to the ecliptic, the most inclined of all large trans-Neptunian objects. Next, Makemake, discovered in 2005 and named for the Rapa Nui creator god. Makemake measures 1,400 kilometers across, making it the largest classical Kuiper Belt object. Its surface shows bright methane, ethane, and water ice, giving it a reddish-brown color. A small moon was discovered orbiting Makemake in 2015, helping scientists determine the system's mass. Makemake rotates once every 22.5 hours. It orbits at about 45 astronomical units with a period of about 307 years. Like Eris, its surface is remarkably bright and fresh, suggesting ongoing resurfacing or sublimation processes. Then there is Haumea, perhaps the strangest large object in the solar system. Haumea is not round. It is shaped like a flattened ellipsoid, about 2,000 by 1,500 by 1,000 kilometers. And it spins. Once every 4 hours, the fastest rotation of any large solar system body. This rapid spin flattens it further, creating its rugby ball shape. Haumea has 2 moons and, remarkably, a ring system discovered in 2017. It was the first ring ever found around a trans-Neptunian object. The surface consists of nearly pure water ice, unusually bright for a Kuiper Belt object. These properties suggest Haumea experienced a massive collision that created a family of related objects. Wow orbits at 44 astronomical units with a nearly circular path. It measures about 1,100 kilometers across. Its surface contains crystalline water ice, ammonia hydrate, and small amounts of methane. A moon named Weywut, about 170 kilometers across, orbits the dwarf planet. But most remarkably, Quaoar possesses rings. 2 rings were discovered in 2023, lying surprisingly outside the Roche limit, where tidal forces should disrupt ring particles. How the rings remain stable is not yet understood. In 2025, observations revealed possible evidence of a second moon or dense ring arc. Every new discovery about Quaoar raises new questions. Gonggong orbits on a highly eccentric path from 34 to 101 astronomical units over 554 years. It measures 1,230 kilometers across and shows a very red color from tholins on its surface. Recent observations detected significant ethane ice along with water ice and methanol. Gonggong has a moon, Shengliu, about 100 kilometers across. The moon likely slowed Gonggong's rotation through tidal forces. The red color is among the most intense of any solar system object. Understanding what creates and maintains this color helps us understand organic chemistry throughout the outer solar system and around other stars. And finally, Sedna, perhaps the most mysterious of all. Sedna's orbit is extreme. Its perihelion, closest approach to the Sun, is 76 astronomical units. Its aphelion, farthest distance, is 937 astronomical units. One complete orbit takes 11,400 years. Sedna never comes close enough to Neptune for that planet to have influenced it. So, what puts Sedna on such an orbit? Perhaps a stellar encounter billions of years ago. Perhaps an ejected planet. Perhaps the hypothetical planet 9. Sedna's very existence tells us the solar system's history is more complex than we thought. More violent, more dynamic, more full of surprises. Each of these worlds likely harbors its own secrets. Do they possess subsurface oceans like Pluto might? Are they geologically active or long dead? What does their varied chemistry tell us about conditions in the early solar system? We know so little because they are so far away, so difficult to observe. But each discovery expands our understanding. Each measurement adds to our knowledge. And perhaps someday, we will send spacecraft to visit these distant worlds, to see them up close as we saw Pluto, to uncover their mysteries, to learn their stories. Until then, they remain enigmas in the darkness, calling to our curiosity. Could there be another planet in our solar system? A world we have never seen, lurking in the darkness beyond the Kuiper Belt? It sounds like science fiction, but some astronomers believe such a planet exists. They call it Planet 9. Not the ninth planet, since Pluto held that title, but an entirely new world, perhaps 5 to 7 times Earth's mass. A Neptune-sized planet orbiting 200 to 1200 astronomical units from the Sun. So distant that one orbit might take 10 to 20,000 years. Let me show you the evidence that hints at its existence and the mystery surrounding this hypothetical world. The first clue comes from orbital clustering. 6 extreme Neptunian objects with semi-major axes exceeding 250 astronomical units show similar orbital orientations. Their arguments of perihelion and longitudes of ascending node cluster together. The probability this is random is only about 4%. Something seems to be shepherding these orbits, keeping them aligned. Computer simulations suggest a Neptune-mass planet in the outer solar system could create exactly this pattern through gravitational perturbations over millions of years. The planet would herd these distant objects into similar orbital configurations, just as a shepherd guides a flock. A second clue involves orbital plane warping. The Kuiper Belt's orbital plane should align with the plane of the inner solar system. But observations of more than 150 Kuiper Belt objects reveal the plane warps beyond 80 to 200 astronomical units. It tilts away from the invariable plane of the solar system. This warping could result from a distant, massive planet whose inclined orbit gradually torques the entire Kuiper Belt. The required planet mass and orbital parameters match those predicted by the clustering evidence. 2 independent lines of evidence pointing toward the same conclusion. Coincidence? Or reality? Some trans-Neptunian objects have perpendicular or even retrograde orbits, moving opposite to the planets. These orbits are difficult to explain through the solar system's known dynamics, but simulations show Planet 9 could naturally produce them. As objects interact with the planet over many orbits, some get flipped into high inclination or even retrograde configurations. The existence of these objects was predicted before they were found. That predictive power lends credibility to the Planet 9 hypothesis. When a theory successfully predicts observations before they are made, scientists take notice. It suggests the theory captures something real about nature. Detached objects like Sedna provide another clue. These bodies have perihelia too distant for Neptune to have influenced. How did they get their current orbits? Planet 9 offers an explanation. As it orbits, its gravity would slowly pull classical Kuiper Belt objects away from Neptune's influence, detaching them. The number and orbital properties of detached objects match predictions from Planet 9 models. Additionally, 5 objects may be in mean motion. Resonances with Planet 9, similar to how Pluto's are in resonance with Neptune. The resonances would arise naturally from the planet's orbital period and gravitational influence, but not everyone accepts the Planet 9 hypothesis. Some astronomers argue the sample size is too small to draw conclusions. Perhaps observational biases create the apparent clustering. We preferentially discover objects in certain regions of sky, which might create false patterns. Others suggest a self-gravitating disk of aligned objects totaling 10 Earth masses could produce similar effects without requiring a planet. Or perhaps our gravitational theory needs modification at these extreme distances. Captured primordial black holes, stellar interactions during the Sun's birth cluster phase, and other exotic explanations have been proposed. The debate continues. The mystery may soon be resolved. The Vera Rubin Observatory began operations in 2025, conducting a comprehensive sky survey. Over the next decade, it will discover tens of thousands of new trans-Neptunian objects, mapping the outer solar system in unprecedented detail. If Planet 9 exists and is brighter than magnitude 22, Rubin Observatory should find it by around 2035. If it does not find it, the hypothesis will be seriously challenged. Either way, we will know. The unknown will become known. And whether Planet 9 exists or not, the search will reveal wonders. Because every time we look deeper into the darkness, we find that the universe has more to show us than we imagined. The story of Pluto begins nearly a century ago with a young man and a telescope. Clyde Tombaugh was 24 years old, raised on a Kansas farm with no formal education beyond high school. But he loved astronomy. He built his own telescopes and sketched planets with remarkable skill. Those drawings impressed the astronomers at Lowell Observatory enough to offer him a job. His task was to continue Percival Lowell's search for a hypothesized ninth planet beyond Neptune. For months, Tombaugh photographed the night sky, section by section, comparing images taken nights apart, looking for anything that moved. On the afternoon of February 18, 1930, Tombaugh examined plates of the constellation Gemini taken in late January. For 3 hours that morning, he had seen nothing. But at 4 in the afternoon, he spotted something. A faint dot that appeared in one position on one plate and a slightly different position on another. His heart raced. He checked backup plates. The movement was real. He walked calmly across the campus to tell Director Vestoslaifa, "I have found your Planet X," he said. The search begun by Percival Lowell decades earlier was over. A new world had joined humanity's family of known planets. The announcement came on March 13, 1930, the anniversary of both Percival Lowell's birth and William Herschel's discovery of Uranus. News telegraphed around the world electrified the public. New planet. The first discovered by an American. The first found through systematic photographic survey. More than 1,000 names were suggested. Pluto, proposed by an 11-year-old English schoolgirl named Venetia Burney, was chosen. The name honored the Roman god of the underworld, appropriate for a world in the outer darkness. And cleverly, the first 2 letters were Percival Lowell's initials. The name was officially adopted on May 1, 1930. For 76 years, Pluto reigned as the 9th planet. Children memorized the planets ending with Pluto. My very educated mother just served us 9 pizzas. The doubts grew. Observations showed Pluto was far smaller than expected. The discovery of its moon, Charon, in 1978, enabled mass measurements revealing a world smaller than Earth's moon. In the 1990s, astronomers began finding other objects beyond Neptune. The Kuiper Belt was real, not hypothetical. And Pluto began to look less like a planet and more like the largest member of a new population. The discovery of Eris in 2005, larger and more massive than Pluto, forced a reckoning. In August 2006, the International Astronomical Union met in Prague to settle the question. What defines a planet? The debate was contentious. The initial proposal would have expanded the solar system to 12 planets. But the final vote on August 24th narrowed the definition instead. A planet must orbit the sun, be massive enough to be round, and have cleared its orbital neighborhood of other debris. Pluto met the first 2 criteria but failed the third. Its mass is only 7% of the combined mass of other objects in its orbital zone. It was reclassified as a dwarf planet. Only 424 astronomers voted, a tiny fraction of the world's astronomers. The controversy has never truly ended. The public reaction was intense. People who grew up learning 9 planets felt genuine sadness at the change. School students protested. State legislatures responded, with New Mexico and Arizona declaring Pluto a planet within their borders. Musicians wrote songs. The American Dialect Society named Pluto its word of the year, meaning to demote or devalue someone or something. Many planetary scientists rejected the definition, arguing for a geophysical classification based on properties rather than orbital dynamics. The debate continues today. But regardless of classification, Pluto itself remains unchanged. A fascinating world worthy of study, regardless of what we call it. But there is more to the Kuiper Belt's history. Gerard Kuiper, for whom the belt is named, predicted in 1951 that icy bodies might exist beyond Neptune. Kenneth Edgeworth independently made similar predictions in the 1940s. Julio Fernandez made the most accurate prediction in 1980, suggesting a comet belt as the source of short-period comets. But the belt remained hypothetical until 1992. David Jewett and Jane Liu, using CCD cameras at Mauna Kea, discovered the first Kuiper Belt object after Pluto and Charon. They named it 1992 QB1, though it is now officially called Albion. That discovery confirmed the belt's existence and opened a new era of outer solar system exploration. A 62-year gap between Pluto and the belt's confirmation. What the wait? What have we learned from our journey to Pluto and the Kuiper Belt? First, that distance from the Sun does not determine whether a world is interesting or active. We assumed the outer solar system would be cold and dead. We were wrong. Pluto possesses flowing glaciers, towering mountains, possible ice volcanoes, and likely a subsurface ocean. All of this on a world receiving 1,000th Earth sunlight. If Pluto can be active at 40 astronomical units, what about the more distant Kuiper Belt objects? What about icy moons around other stars? We have expanded our understanding of where dynamic geology can occur. Second, we have learned that ocean worlds may be common. If Pluto harbors a subsurface ocean maintained by internal heat alone, with no tidal heating from a giant planet, then ocean worlds might exist throughout the outer solar system. Every dwarf planet with sufficient rock for radioactive decay and sufficient ice for insulation could potentially maintain liquid water. That means there could be dozens of ocean worlds just in our solar system's Kuiper Belt. Extend that to Kuiper Belt analogs around other stars, and the number becomes astronomical. Ocean worlds might be the norm, not the exception. And oceans are where life on Earth began. Third, New Horizons taught us about planetesimal formation. The flyby of Arakoth in 2009 revealed a pristine contact binary that formed through gentle gravitational collapse, not violent collision. The uniform size of surface mounds suggests planetesimals form with preferred scales. This validates streaming instability models and overturns decades of hierarchical accretion theory. Understanding how planetesimals form in our solar system informs our understanding of planet formation around every star. The building blocks are the same everywhere. The processes are universal. What we learn here applies across the galaxy. Fourth, we have learned about atmospheric processes at extreme conditions. Pluto's atmosphere exists despite surface pressure 100,000 times less than Earth's. It extends 1,600 kilometers high, despite gravity that should compact it. Solid-state convection in nitrogen ice, driven by surface cooling, represents a new convective mechanism. Methane dunes form in near vacuum. Organic hazes create complex molecules that rain onto the surface. Every measurement reveals physics operating at the limits of our experience, expanding our understanding of how atmospheres work everywhere. Fifth, the Kuiper Belt preserves the solar system's history. These objects are time capsules, frozen remnants from 4.6 billion years ago. Their compositions tell us what ices were available where, what temperatures existed at different distances, what the solar nebula was like. Their orbits record Neptune's migration and the violent dynamical evolution that scattered 99% of the original belt. Every measurement, every new discovery adds to our understanding of where we came from. How the Sun's planetary system formed and evolved. What conditions were like when Earth and the other rocky planets were just forming. Sixth, we have learned humility. For decades, we underestimated Pluto. We assumed small meant simple and boring. We assumed distant meant irrelevant. We were wrong on both counts. This should teach us caution about dismissing other worlds, about assuming we understand something before we have seen it up close. The universe consistently proves more complex, more surprising, more wonderful than our imaginations predict. Every time we look, we find something unexpected. Every time we visit a world, it exceeds our expectations. This pattern should inform our approach to future exploration. Expect the unexpected, because nature's creativity surpasses our own. Finally, we have learned that exploration matters. The knowledge we gain enriches humanity. The images we capture inspire the next generation of scientists. The technology we develop finds applications beyond spaceflight. The international cooperation required builds connections between nations. And the simple act of reaching beyond our world, of touching the distant and unknown, feeds something deep in the human spirit. We are explorers. We are curious. We look at the horizon and wonder what lies beyond. Pluto reminds us why we explore, not for economic gain or military advantage, but because we must, because we are human, and the unknown calls to us. Our journey to the edge of the solar system is complete. We have traveled 3 billion miles, seen wonders we never imagined, and learned that the frozen frontier is anything but dead. Pluto lives, geologically active and complex. Charon records the transformation from ocean world to frozen corpse. The Kuiper Belt preserves the building blocks of planets. And somewhere in the darkness, perhaps Planet 9 lurks, waiting to be found. But this is not an ending. New Horizons continues outward, still exploring, still discovering. Future missions will return to these distant realms. And you, having taken this journey with me, carry knowledge of these wonders. The next time you look up at the night sky, remember. Billions of kilometers away, a small world dances with its moon in the eternal dark. A world with a heart of ice and secrets we are only beginning to uncover. Thank you for joining me. May your dreams be as vast as space itself.